Good morning, or good afternoon, or even good evening, depending on where you're joining us from today. My name is Chuck Tatham. I am not on camera. That's why Andrew's mouth is not moving. But I am here to kick off our session, a bit of a tongue-in-cheek title, covered by Andrew Hillier, our CTO and one of the co-founders of Densify.
Thanks, Chuck, and thanks everyone for joining. Chuck always puts pressure on me to be funny, but we thought we'd be funny with the title this time, so I don't have to be. And it's really, this whole notion of optimization techniques that cloud providers hate. Cloud providers are generally interested in people getting their money's worth out of their product and that type of thing, but there's certain things they're not overly eager to help you fix, and I'm going to walk through some of these things because they kind of do benefit from them. So the premise here is that I don't think anybody minds if you give them money. I mean, that's kind of great, right? It's the business model. So cloud provider probably no exception. If you're spending a lot with them, they like to help you, but only so far. And they also, and I'll cover this in detail, they don't mind if you run on older stuff. They've got new stuff, they've got old stuff. If you're staying on the old stuff, they paid for it years ago. That's not so bad for them. It might be okay for you, might not. So I'm going to go through that in a bit of detail. And then, containers themselves can be quite inefficient. And overall, so again, the three things I'm going to cover are: get off the old gear unless it's your intention, but don't accidentally be on old gear because you just ignored it. One point there. Stop oversizing containers. If you make them big, it does make a huge cost problem. And then optimize your container nodes. And I'll talk a bit about nodes themselves, and then scale groups in the cloud where the nodes typically run, and kind of what ways of looking at that to help stop driving waste, excess costs, and also, again, get off the old stuff. All right, stop using old stuff. Again, like, unless it's your intention. And the analogy here is, it's kind of like if you get in a taxi that's 15 years old, I mean, you could also get a new taxi for the same money, but maybe the taxi driver likes driving his car into the ground, but it's not necessarily good for you. That same thing happens in the cloud quite a lot. And I'll start by talking about why a lot of it happens. It may not be intentional. It may be that it's just difficult to figure out which instances to use in the cloud. I'll pick on Azure first. I'll pick on all three cloud providers, the major ones. If you're on a standard DS4 V2, that's a pretty old instance. I don't know the exact year that one came out, but it's pretty old. And it's an 8 by 28 for whatever reason at the time. They made it a 28. And you need to figure out, what to do with this, because maybe it's really not the newest, and it may not even be the optimal instance, but it's very hard. So there was a DS4, but that's going backwards. You rarely want to go even older. DS4 V3 does seem like the logical newer thing that you could go to, but you can't because that never existed for whatever reason. This slide starts to get a bit comical, actually, if when you go through it. There is a D4S V3, which has a lot of the same letters in a different order and newer number, but it's only a 4 by 16. Who knows why? There's a D8S V3, which is actually a 4 by 32 at this point, but it's still pretty old. It's a V3. I think the D5s are out now. So what about a D8S V4? Let's go a little newer on that one. Nope, doesn't have a disk. They took the disk away in that rev. The D8DS V4 became the thing with a disk, which would work, and a D8DS V5 is the newest. So, I mean, this is just one example. It's very difficult to pick the right instance for a workload. It might be wrong because you might not even, that DS4 might not have been the right thing in the first place. Maybe, oh, I should mention, even this, we had this happen in a customer where this new thing doesn't have the same number of disks or network adapters, and that was a problem for them. So even that's the level of detail you need to go down to figure out, what you can run on. I'm not going to go through how we do that in this webcast. It's not about us. It's about the problem that you have trouble figuring this out. You're probably going to stay on the old stuff. It's too hard to figure out what to do with it. And again, that's not even considering there's all kinds of other options that might be even better for that workload. Going to a memory optimized is often a good idea, or a burstable for certain types of workloads. And the idea is that in Azure anyway, and as of last year, there were over 600 options, VM size and type options. It's probably the perfect thing for your workload, and you're probably never going to find it. And the topic today is you're probably just going to stay on old stuff. Oh, sorry, I have a note to self still on the slide. Here's an example. This is an actual environment. The y-axis is how much CPU hours are running, and the x-axis is by how old the gear is. So this particular environment, about 2/3 of the environment is running on gear that's 9 years old. It's kind of crazy. It's just riding off into the sunset because nobody's going back to look at it, or because the Terraform file has whatever it is, like an M3 stuck in it. Again, there's no process to go and change that. So we see this as a pretty big problem. I mean, it might make sense if those things are super cheap, but quite often we find when newer instance types come out, they're kind of the same price. They're just better and faster. So there's not really a big excuse to be running on 9-year-old gear. My note to self here is that if your laptop was 9 years old, you probably wouldn't be too happy that you're sitting on a 9-year-old laptop. There's not really a good reason to do that in the cloud. either. I think that's an Amazon example. I'm an equal opportunity criticizer. I think this is an Amazon environment, and GCP has an interesting feature that also creates a problem in that underneath the instance types in Google, you can have all kinds of different processors. Like the other providers tend to make the instance type have a specific architecture under it, but Google kind of abstracts it more. So like an N1 can have all kinds of options under it, and you're probably not on the latest one. You can actually ask to be on a certain one, but most people don't know that or don't have a way to do that. Like if you're running on an N1, you can ask for Skylake, but I don't think we've seen anybody really doing that. And in this case, the Skylake is 4 years newer than the Sandy Bridge architecture for the same money, for the exact same money. So there's not really any excuse. If you ask for that, it's only advantage to you. Of course, for the person that owns that data center and has a lot of old gear in it, it's great. If you keep using it, they paid for it, whatever, 9 years ago, they'll just happily let you keep using it until it fails. If you go between families, it's even worse. So the Ice Lake in an N2 is actually 8 years newer than the oldest N1, and it's almost the exact same price. It's 22.5 roughly cents an hour instead of 22 cents an hour. So again, going to an N2 Ice Lake confers quite a bit of advantage for a little tiny bit of money, or even just the newest in the N1s. It just makes sense to do that. But most people don't have time to look at it. And so you're running on really old stuff. It's like driving around in really old taxis that the same money would get you a new one. And they perform better. It's not just kind of nicer. It's actually workloads will work better. That's Azure, Amazon, and Google with 3 different views, but the same kind of notion. And in this case, in Google, you can actually ask for, like I said, here's a recommendation onto an N2 standard 2 Ice Lake. You just have to qualify it when you ask for it. They ask for Ice Lake and you get it if it's available in the region. Again, the workload's going to work better. In this case, we're downsizing at the same time, but you're still getting a bump. We're going from let me go back here, an 8-way to a 2-way, but a newer version of it, and your workload fits just fine. All kinds of advantages if you have. We call that a modernize. There's different strategies for that, but just get on the newest stuff and the right size stuff. I'll call out one more thing here because we do a lot of work with Intel. I'll talk about it towards the end. First here, you can actually ask for that Ice Lake in the second line of this code here. Again, a lot of people don't know that. Not only ask for the N2, but you can say, give me an Ice Lake N2, and you can do it through this is Terraform as an example, or through the UI. So again, not really good reason not to do that. The latest Sapphire Rapid CPUs from Intel are now available in C3s in Google GCP. And they're only 25 cents an hour, and they're way newer. So again, I know I'm piling it on here, but get on the latest stuff. It's to your advantage for pretty much the same money. This one's 3 cents more. These things have a lot of accelerators that will probably make your workloads go much faster as well. What I just covered is not specific to containers. It's relevant to containers, absolutely, but it's for any cloud workload. Specific to containers, we find that there's a problem that people tend to make them the wrong sizes, and usually too big, but often too small as well. It's a bit of a mix. And to illustrate that, so the problem here with a container now is that if I have this specification of the CPU and the memory resources, the requests and limits, this is what tells Kubernetes in this case to go and this thing's going to need a half a gig of memory and 2 CPUs, and limit me if I go above a certain amount. And that's what it uses to provision you, and it kind of gives you those resources. You share to a degree, but when it's scheduling, it makes sure you will get those resources. And the problem is somebody has to put these numbers in, and they don't know what to put. And it's not their fault. Like how would you know when you're deploying it? Unless you have really good telemetry off the running systems and you look at it every day, you're not really going to understand what the thing should be. As a result, what happens is it tends to look like this. And these are real examples. This is the CPU utilization curve for a container. And the request and limit are both set to 2,000 millicores or 2 CPUs. And this thing's not even using a fraction of that. So you're way too big. You asked for 2 CPUs, and the problem is, again, you're kind of getting 2 CPUs when Kubernetes schedules. It will once it gives out all the CPUs, it moves on to a new node. So you're going to strand a lot of capacity with this configuration. At the same time, and it could even be in the same instance, this one has a memory request of 1 gig, and it's using upwards of 3. It's fluctuating between 2 and 3. I should point out these are quartiles by hour of day. So this is the operational pattern of this workload. It's the peak is the very top of the thin zone, the minimum is the bottom of the thin zone, and then the workload spends half its time in the thick zone and the median, and I won't get to all the math, but this is how we model the fact that this workload fluctuates all day over 24 hours between 2 and 3 gig of memory usage, and the CPU fluctuates throughout the day as well. Even in the same container, you can be wrong in 2 different directions, and in the same pod, you can have multiple containers, and so on and so on. So this can become a pretty big problem. And what happens when you do this is you have this mix, and we kind of came up with a way to visualize this, which I think is pretty important because container environments can be pretty big. So here's an example where the request, that's one I just showed, the container is given a third of the resource, a third of the memory it actually needs. And so we can actually chart that on a kind of a histogram saying you're down in this red zone, meaning you're undersized. You only have a third of the resources that you actually should have. Here's one that's been given 5 times more memory than it needs. It's using 100 meg, and it's been given 500 meg. So it's over in this 500%, 5 times too big bucket, 500 and up. Here's one that's pretty good. It's been given about 800 meg, it looks like, and it's using upwards of 750 at peak memory usage. We would drop that in the middle, saying that one's just right. No, it's like Goldilocks. And the fourth scenario we see is that you didn't give a value at all, which is pretty dangerous in container environments. We'll show that over in this unspecified bar as gray. And if you do this in scale, and we can do this at any scale, you get a visualization of a running environment looking at the profile. And in this case, a bunch, about 108 or so, it looks like containers are good, but there are so many that are way too small and almost an equal number that are way too big. So everything's wrong kind of in all directions. Not everything, but 2/3 of the environment is wrong in one direction or the other. And this is exactly what we see in environments. They're all over the place, right? They're too big, they're too small, that kind of stuff. With that in mind, you can step back and look at, some pretty big, you can do this on an app, you can do it on a component like a, Nginx. You can look at all your Nginx across your organization, a business unit, a subscription in the cloud, a container environment, whatever that is. This is a whole company. This is everything they have running in Azure, I believe it is. Doesn't really matter which cloud provider it is. And CPU requests, memory requests across the top, CPU limits and memory limits. And the takeaway from this, I won't go through in detail. We have other webcasts that talk about this in detail, but I'm just skimming across the surface now. But in this environment, I think there's about 14,000 containers, and 4,500 of them, roughly, are over 5 times too big. Like, it's pretty crazy, but we see this everywhere. It's not uncommon. At the same time, we've got about 1,000 containers that have 1/5 of the memory that they need, which is very dangerous. And a whole lot of containers are too small. This is the 1/5 or less, meaning they're egregiously undersized. That's kind of balanced by the fact that there are thousands that are way too big. And this is what, in this environment, this is kind of saving you. The fact that you're not asking for enough on some and too much on the other, hopefully they land together in the same box and you don't blow up your node. I'll get back to that in a second. So you got things that are way too small, things that are way too big. You've got things that don't have limits. So if you have a bunch of these, then a memory leak can kill a node. Like, there's all kinds, again, we've done webcasts on that as well, just really detailed into unspecified resources. So if you're interested in that, you can find a whole recording of a webcast on that itself. But I wanted to focus today on this one, which is you just oversize things pretty badly for CPU. And the impact of that is that here's a cluster, and this is the utilization over a bunch of days. This is a while ago, where this is the request value. So on the nodes in the cluster as a whole, I'm giving out 80 to 90% of the resources to the containers, which is great. That means Kubernetes is scheduling things, giving out resources on the nodes. But the utilization of this environment was averaging 7%. And we oddly see this number quite a lot, around 7, 6, 7, 8%. You're just not using the resources, but you're paying for all this on the floor or in your scale groups, and you're just not using it. So containers can start to become extremely expensive if they're sizing correctly. The problem, and again, I won't get into it today, we have other webcasts that cover this as well, is that this does not overcommit. It's not like a VMware environment where you can give the same CPU out to multiple workloads. These are not virtual resources. So when it goes out, you schedule a node. If you ask for a CPU, the scheduler gives you a CPU. You can use more if nobody else is using them, or they can use your CPU. But the node, when you've given out all the CPUs on a node, you move on to the next node. And so you end up with really, really low utilization. And we see this everywhere. Even the most sophisticated container environments have a ton of stranded capacity, which means high cost, which means you're running a lot of gear from your cloud provider that you don't need to be. And again, back to the topic, maybe they don't mind that. Maybe they're not really in a hurry to help you fix this, but it makes container environments be expensive when they don't need to be. Which gets on to the third one. This is kind of at the node level now. I kind of talked about containers, and then you get to the node level, it means that your nodes aren't well utilized. Let's dig a bit deeper. Not only are they not utilized, but if I have something that looks like this, I've got a whole bunch of memory, containers that are too small, a whole bunch that are too big. Kubernetes doesn't know what to do with them. If you only ask for 100 meg, but you need a gig, it's going to schedule like you need 100 meg, and it could put a whole bunch of undersized ones on the same node, and the node blows up. Or it could put a bunch of oversized ones together, and you have really underutilized nodes, and that's exactly what happens. So this is a set of worker nodes. This particular example is in Azure. It happened to be running, and it doesn't really matter what cloud provider it's in, it works the same way. This one had 72 worker nodes in a pretty big cluster, and the peak and average memory utilization was all over the place in the nodes. And if we sort that, we can see that the top nodes were really pretty much hitting the roof. You can't really get above that. For example, this top one was flirting with 100%. That's when things start getting killed, and things were getting killed in this environment. So some nodes are running at 100% or as close as you can get before things crash. At the bottom of the list, the bottom ones weren't using much memory at all. This one was using 15% in the same cluster, in the same node group. So it just makes a mess of the nodes if the container sizes are wrong. You're going to end up buying big nodes to stop kills from happening, because like I said, in this environment, kills were happening. And you'll end up oversizing even worse because it's just a mess, even though there's plenty of capacity in this environment if the pods were placed on the right nodes. But Kubernetes can't do that when the values are wrong. The last thing I'll mention in this run is that the scale groups, that would be running on the scale group or a scale set in that case in Azure. This is an Amazon example of the scale groups. So this is what the containers run on. And I'll highlight this one here because there's a whole bunch of things wrong with this. It's currently the node type is a C4 large. And I'll just bring up this build. C4 large is, I mean, they actually don't seem that old intuitively, but they are. They're from 2015. So that's like 8-year-old. We're recommending put it on an M6i, which is much, much newer. It's also compute optimized, but you don't need all that compute. It's not being used. So we're saying go to general purpose, and then you'll get it much better. So not only is it old, it's the wrong size. It's too much. It's too big. There's too much CPU in this node type. And the scaling parameters are min 4, max 4. And we're saying, well, that's just going to pin you at 4. By analyzing the workload, you could go as low as 2 and as high as 5 throughout the day. And that's this curve right here. So not only are you old and the wrong size, you're not elastic. You're just pinned at 4 nodes. Your workload, you would actually scale down to 2, for example, overnight or whenever you have low periods, if you open this up. So there's just some recommendations for the actual scale groups, which are the nodes in the container environment. So all these things kind of chain together. They're too old, they're the wrong size. The containers are probably the wrong size in here. If you optimize the containers, you probably get an even different answer here. And the net is what it looks like. Let's close it off with this kind of Tetris style diagram. Picture the containers or the pods. The workload is these Tetris blocks. Some are busy in the morning, some are busy at night or midday. The dotted lines are the allocations. That's what you're asking for. So when you ask for these request values, that's kind of the dotted line. If you ask for too much, you get low density on the nodes. But if we take that and say, well, let's look at what they're actually doing and optimize those values, and usually it's downward, it can be upward, you saw the histograms. The next time they redeploy, the requests will be more in line with what the workloads actually need, and Kubernetes will automatically stack more on each node. So you'll just get an immediate hit because Kubernetes is able to more intelligently place things. You're not tying its hands behind its back, but by giving it these big resources. So in PowerPoint terms, we knocked off 1/3 of our cost by just getting rid of nodes. Then the nodes themselves might not even be the right nodes, as I just showed. This is an Azure example where we can be moving to a memory optimized, and we'll run, in this case, fewer of them because we're giving them more memory. And then the third step is that's still a V4. If I go to a V5, I'll get probably an additional bump. I don't show it in PowerPoint here, but it's all three of these concepts kind of working together in the container environment. And again, if you stay running on really old stuff and way too much of it, it's really your problem. Nobody's really going to magically help you fix that. Obviously, we have analytics to do that, but I mean, the cloud providers aren't going to just step in and say, we want you to stop using so much of our gear. And that's really the parting thought, is that they're not really going to do this for you. They just have, pretty basic advisors. They don't really, tackle that elasticity problem I showed. If you spend too much, it really, only benefits them, and that makes sense. And if you low gear, it also only benefits them. If they can drive you around in 10-year-old taxis and they can get away with it, that's, I'd keep doing that. So that's really kind of back to the whole theme here. And again, it's a bit of tongue in cheek that, the cloud providers really hate it, but these are really practical considerations when running containers. I mentioned we do a lot of work with Intel. Intel actually offers our product as Intel Cloud Optimizer. It's a pretty cool program, and they actually will fund its use for qualifying customers. So if you're interested, there's a QR code. We do have a poster, and like I mentioned, we do lots of webcasts. We did an entire webcast on these 12 problems that you get with too big, too small, for request limits, that type of thing. So there's a poster actually that shows these things. The new thing, I've been hosting a new podcast where we talk to our customers, and we find that great because our customers do some really cool stuff in this area directly related to what I've been talking about, and cloud and containers. And so if you're interested in that, there's, I think, 2 episodes. A third one we're working on, so it'll be out soon. One common question is, what we cover. I think it's probably implicit in what I talked about is, we optimize Kubernetes environments. We do have ECS optimization as well, but mostly we see customers doing Kubernetes. And across the big 3 cloud providers, we focus on Amazon, Google, and Azure. Again, that's across those, what I described is kind of uniform across those different providers. Kubernetes environments are obviously growing like mad. So we see that this problem, when we describe it, is kind of early in some customers. Some are starting to realize it. Maybe some are getting the bill from their container environment. And so we're seeing a pretty significant ramping around the attention every day. We see more and more focus on the container environments as they grow and go into production.
Thank you all for attending, and have a great day.